For this lesson, we're going to be continuing our examination of trigonometric equations and how to solve them. The big difference here is that we're going to be looking at equations that are not necessarily order 1. So generally quadratic, meaning order 2. A lot of the steps are going to be similar to what we've done before when we were solving linear quadratic equations, but there are going to be some differences. One of the big differences is the number of solutions has the potential to really get out of hand with these. And how you approach them, there's more ways that you can try to solve these, and so you can go down more blind alleys. So be aware that you might have to backtrack a bit or you might have to try a different strategy. And in that way, it's a bit like doing a trig identity. You might have to do a little bit of trial and error. Another big element is when we're solving anything that's higher order, generally we're looking to solve for zeros. So you're going to want to rearrange these in general so that one side is equal to 0. Not always true, but in general. And I think I have an example here where I have a number of examples where that is true, but I have at least one example where we won't necessarily be looking for that. Factoring will probably be involved. It won't always be involved, but it will probably be involved. And I mean both common factoring and other types of traditional factoring around quadratics, which may also include the quadratic formula. Whenever you are dealing with a factor, each individual factor should only involve one trig ratio. The overall equation may actually have multiple trig ratios, but each individual factor that you hope to solve, you need to reduce that down to a single trig ratio. And again, we're going to be looking at a number of ways to do that. Then we get into some very typical solving of linear equations. We solve for the related acute angle. It's just we have to do that for every ratio or factor that we have. We apply the cast rule, and then we take a look at any restrictions on the domain. That's going to tell us how many angles we have, and then we determine our angles themselves. Okay, so let's go ahead. Other than that, let's just dive right into a few examples. So solve each equation for 0 less than or equal to theta less than or equal to 2 pi. So basically one full rotation. Now this first one, and I intentionally chose some of these to give you a moment of pause. So just take a look at that at first. See what jumps out at you and what direction you might go, and just be aware that there are wrong directions to go here. And when I look at this, the first thing I see, but it actually is a wrong direction, is 2 sine theta cos theta is the same as sine 2 theta. Now if I were to introduce this correctly using the trig identity, now I've got a term in theta and I've got another one in 2 theta. That's not helpful at all. So be prepared to either go through this mentally, make those mistakes, and then backtrack, or try some different things. So what I'm going to do in this case is I'm actually going to use another piece of advice that I provided on the previous page, which is I'm going to move everything to one side. So I get 2 sine theta cos theta minus cos theta, and that's equal to 0. And now taking a look here, what you hopefully notice is that there is a common factor of cos theta. There's nothing that says I have to get rid of the sine theta or the cos theta. What I have to do is I have to try to create factors that only have one ratio. So if I factor out my cos theta, I end up with 2 sine theta minus 1. My factor number 1 is in terms of cos theta. My factor number 2 is in terms of sine theta. So each of these individually only has one trigonometric ratio. So that means I should be able to proceed. Now can I proceed? I've got something times something. I'm multiplying two factors together and that's equal to 0. That means that one of those, so number 1 means that either cosine of theta is equal to 0, or for number 2 it means that 2 sine theta minus 1 is equal to 0. And now I'm going to solve each of these two possibilities. Now cosine theta equal to 0, this is going to be something that's on one of the axes. And just try to remember that any point is written in terms of cos theta sine theta, meaning the cosine theta is the x coordinate. So for what angles do I have an x-coordinate equal to 0? So where's the x-coordinate equal to 0? On the unit circle, it's going to be this point, and it's going to be this point. And this first point, the one here at the top, that represents an angle of pi by 2. And this one at the bottom represents an angle of 3 pi by 2. So those are my two options. Now we go over here, and I'll come back to this for just a moment. I don't need to consider multiple rotations around because the initial condition said that the angle was between 0 and 2 pi. So I only have to consider one rotation here. Now let's come over to this second equation, which I'm going to rearrange to be 2 sine theta equals 1, sine theta equals 1/2. And so what value of theta gives me a ratio of a half? And if you remember your special triangles, 1 to root 3, pi over 6, pi over 3, and from here we can see that the sine of pi by 6, opposite over hypotenuse, gives me a half. So the way I'm going to do this, I'm going to do it the same way I try to do our other problems like this. First, I'm going to find the related acute angle. Now, since this is positive already, well, that's fine, but the related acute angle in this case is pi by 6. And then I'm going to apply the cast rule. So now that I know the related acute angle, and I ask myself, well, where is sine positive? Sine is positive in quadrant 1 or quadrant 2. So now that I have that, now I know my values for theta in quadrant 1. Well, the value for theta in quadrant 1 is simply the related acute angle, which is pi by 6. And in quadrant 2, my value for theta is going to be pi minus the related acute angle, which is pi by 6, which works out to be 5 pi by 6. So as you can see here, I actually ended up with 4 possible solutions, 3 and 4, and all of those are valid. Let's go on to our next example. Sine squared theta plus 4 sine theta is equal to 5. The only ratios I have here are sine theta. And so I don't have to do any manipulations to change the ratio, at least I don't think I do, because I've only got one. Now, one thing you might want to do is, well, first of all, let's go ahead and rearrange this for 0. So sine squared theta plus 4 sine theta minus 5 equals 0. So what I've done is I've got a quadratic equation. Some people are still a little intimidated by this form, and so something you might do at this point is you might say, I'm going to let some other variable, in this case we haven't used x, I'm going to let x represent sine theta. And the only reason I do that is because now instead of sine squared theta, I can call that x squared. Instead of 4 sine theta, I can call that 4x. And instead of, well, negative 5 is just a constant, so that stays the same. And this is a very comfortable quadratic equation. And what are two numbers that multiply together to give me negative 5 and add to give me positive 4? And my answers there are going to be x plus 5, x minus 1 equals 0. And then that gives me two solutions. That gives me solutions x equals negative 5 or x equals positive 1. But let's keep in mind that we don't care about x here, we care about sine theta. So this one is actually saying sine theta is equal to negative 5, and this one says sine theta is equal to 1. Now, there's a number of ways you could try this. You could even try putting it in your calculator, but I prefer a slightly more mathematically knowledge-based approach to this, which is, don't forget your graph of sine theta. The graph of sine theta oscillates between negative 1 and positive 1. So is sine theta on its own with no transformations, is it ever equal to negative 5? The answer to that is no. So this has no solutions on this side. So this side has no solution. So now we go to this one. I'll move up here. Sine theta equals 1. And I recognize, just like in our previous example when we had cos theta equal to 0, now I'm saying sine theta is equal to 1. And don't forget that any point can be represented on the unit circle as an x-coordinate of cos theta and a y-coordinate, in this case, of sine theta. So where on the unit circle do I have a y-coordinate of 1? And the answer to that is this point right here, which occurs at pi by 2. So interestingly, here we had a quadratic equation, but we actually ended up only with a single solution, despite the fact that we had valid values between 0 and 2 pi. The only value that actually satisfied this was pi by 2. And then finally, I've got an example that I've taken from the textbook. And in this case, we take a look at it. And the first thing you should notice here is the 2x here and a single x there. So I don't like that. So now, in part A, I suggested that using the double angle formula was a mistake. But in this case, using the double angle formula, I think, is probably a good idea. So let's see where that takes us. We're going to change this into 2 sine x cos x minus 2 cos squared x equals 0. So once again, as I said before, we would like to have a single ratio in each factor, but right now I don't have factors. I've still got this relatively complex equation. So it's an order 2 equation. I need linear factors. So once again, I'm going to do two things here. I'm going to divide everything, I'll factor out. I'm going to factor out a 2 cosine x, because there's a 2 that's common to both, and there's a cos x that's common to both. And then what's left behind here is going to be a sine x minus a cos x, and that's equal to 0. Yeah, I think that's the best way. Rather than, I could have also just divided everything by 2, which was what I was originally going to do, and just eliminate this 2 in the first place. But now that I've written this as a product of factors, 2 times cos x times this entire bracket, so that means, of course, 2 can't be 0, so that means that in the multiplication, either cos x or sine x minus cos x, one of those two factors has to be the thing that's making this 0. So let's look at the first one. Cos x equals 0. And I will once again, and I encourage you to do this as much as you need to, whether you can do it in your head or whether or not you need to write it out each time, as I'm showing you here as a reminder. I'm looking for an x-coordinate of 0. So where do I have an x-coordinate of 0? We've actually seen this answer before, which is we end up with x equals pi over 2, which is this one, or x equals 3 pi over 2. And so there are those two answers. Now this second one is actually quite interesting. I think I'll deal with that over here. I end up with sine x minus cos x equals 0. So I mentioned earlier that generally we want to be solving for zeros here. But now that I'm down to a linear equation, it might actually be useful to think of some other ways. Now the first thing you might do is let's rearrange this and write it as sine x equals cos x. So I'm looking for values of x that cause sine x and cos x to be equal to each other. You might think, one thing you might do is you might just visualize the graphs or sketch out the graphs and try to figure this out. But there's something else you can do here that also works, which is when sine x and cos x are equal to each other, that is the same thing as, and I'm going to realize I'm not going to finish that sentence until I do this. I'm going to divide both sides by cos x, and that says tan x is equal to 1. So when is sine x equal to cos x? That occurs when tan x is equal to 1. And you have options. You can use either of these to solve, because both of them still come down to, well, actually, where is tan x equal to 1? It might be easier to have solved it this way. It depends on who you are. You could certainly use your cast rule here. Actually, you know what? That's the other way you could do it. So let me show you the two methods. Sorry, I rambled a little bit there. So this first one, when is sine x equal to cos x? Well, once again, I'm going to refer to this idea. So I'm going to bring those two things together. So what I'm really asking here, when is sine x equal to cos x on the unit circle, is asking when is the x coordinate the same as the y coordinate. So if we look at the unit circle here, when do I have x coordinates that are the same as the y coordinates? And right there, I have the x and the y the same. And that occurs at what angle? That occurs at pi by 4. And then over here is where they're both negative x and negative y, and they have the same value. And that angle occurs, that's all the way over to here. And this one occurs at pi plus pi by 4, which is equal to 5 pi by 4. Now that's a little bit more of an insightful, a little bit more of an intuitive way. And you might not be comfortable with that. It's not really algebraically rigorous. So here's another way we can do it, which is tan x equals to 1. Well, that's the same as saying the tan of the related acute angle is equal to 1. And so where am I going to get that from? Well, that comes from this triangle. 1, 1, root 2, pi over 4. The tan of pi over 4 is equal to 1. So from there I get my related acute angle is equal to pi over 4. And now that I know my related acute angle, I apply the cast rule, and I ask, where is tangent positive? Tangent is positive in quadrant 1 and in quadrant 3. So my answer in quadrant 1 is simply the related acute angle. Theta is equal to, sorry, I said theta, but I really should have said x and x and x. X is equal to pi over 4 in quadrant 1, and in quadrant 3, which is the other place where tan is positive, x is going to be equal to pi plus the related acute angle, and of course that is 5 pi by 4, which is exactly what we did using this other method. So our answers are here and here, and those were from the first equation, cos x equals 0, or the first factor. And then we ended up with these answers, pi by 4 and 5 pi by 4. And you might wrap this up. I'll do that for this one, especially since this got quite convoluted, quite crowded. Therefore, x is equal to, and I'm just going to list these. And normally, if you're going to take the trouble to list them, good form says you're going to list them in order, lowest to highest. So pi by 4 is the smallest angle, then pi by 2, then 5 pi by 4, and finish off with 3 pi by 2. That or looks kind of awkward there. I think I would just probably go with another comma. So list those as my possible solutions. So there you have it, 3 different nonlinear trigonometric equations, and we use 3 different strategies to solve them. So that's what we have by way of homework. This is quite a bit to deal with. And also, because this work can be incorporating a lot of algebraic techniques, our work on quadratics, factoring, seeing the right path and making the right choices, and sometimes even making the right choice to replace using an identity. They're like identities in that way, which means you can go in a lot of wrong directions. And so one of the things you're going to focus on as you do this homework is actually practicing on selecting the right tool or selecting the right direction in order to take you in some productive direction in the end. Okay, that's it for this lesson. Good luck with that work.